Okay, so we're going to continue the conversation we were having last time, where we're talking about how um, nutrient overloading in the environment stimulates photosynthetic production, which in a sense just represents a high BOD stream of material, which in oxygen-limited environments can cause oxygen consumption. And today we're going to kind of talk about a related topic, which is organic matter overloading. And much of the organic matter has a lot of nutrients in it as well. And so in a way, these two processes are interrelated, and we find stimulation of biological productivity in places with a lot of organic matter waste streams, especially the kinds of discharges that come from agricultural areas and urban areas. There are some categories of organic matter, especially industrial contaminants, contaminants from petroleum spills, for instance, which don't behave in the same way because they don't really contain the nutrients. And we'll talk about them later in the semester. But we're going to talk about kind of discharge of organic matter at the kind of general watershed level, and then we'll look at some specifics, some releases at point sources, and then we'll look at occurrences of hypoxia, and these are mostly in sort of coastal ocean or bays or inlet settings, and then we'll kind of circle back to the role of nutrients in this process. And as I say, these things are kind of interrelated, and we can find individual cases where we have more of one or another thing, the nutrients stimulating growth or the organic matter itself causing enhanced respiration. And in some cases, both of those things happen. So we talked the last time a little bit about nutrients, especially fertilizers, fertilizer elements, nitrogen and phosphorus especially. But these are some of the other things that can be released into the environment that cause a high organic matter waste stream to represent BOD in an oxygen-limited environment. So one of them is sewage, obviously, partially or incompletely treated, detergents and cleaning agents. And this one here, excessive topsoil absorption. So a lot of organic matter in topsoil, some of that organic matter is labile. And any one of these, or in combination or by themselves, will increase the total organic carbon in an environment. So these increases have a direct effect on eutrophication or the processes that lead to them. And we can think about how contaminants come into the environment in a couple of different ways. One of which is what we think of like a point source, end of pipe, specific spill, something that we can isolate to a particular place in time. These tend to be more straightforward to remediate. And we'll talk about remediation methods later in the semester, but when we can identify a place where something's happening, it's easier to go in there and try to mitigate it. More commonly, we have problems from dispersed sources, meaning it's coming from all over the place. Much more difficult to address this because oftentimes it has to do with land use practices at a very broad scale, as well as human behavioral practices, which again happen on a broad scale and are much more difficult to transform. And so these tend to cause kind of watershed-wide shifts in water quality. And I just kind of want to emphasize that whenever we have high organic matter, OM, or TOC, total organic matter, this generally represents high BOD. There are some specific cases where the organic matter is what we call refractory, and this is stuff that comes out of industrial processes primarily. We'll look at an example of that later today, but for the most part, most of the organic matter is biologically labile, biologically reactive, and so therefore respiring organisms use it, and it represents BOD, biological oxygen demand. Okay, so if you take a step back and you think about an unperturbed watershed, then you would say that in general, the higher amount of biological productivity we have, the higher biomass, the higher number of plants and animals living in that ecosystem, then the higher amount of organic matter we're going to find in the environment. You can find variations here in the islands if you go to a sort of a wet and lush watersheds such as Manoa or some of the windward side ones, you compare those to the water flowing out of things, for instance, on the Waianae coast, you'll find much higher total organic carbon here than you will over there. So this is also extends to human perturbed landscapes. And the way it extends to human perturbed landscapes is to think about the more humans there are in the landscape, the more likely we're going to have higher total organic carbon in the water that's running off. You can find exceptions to that rule, but one of the things that we do, in addition to salting and evaporating water, which are things we've talked about before, is we make a lot of waste. And a lot of our waste is in the form of organic matter, and that organic matter inevitably gets into watersheds. So we think about, well, we got all this organic carbon. Some of it is soluble water, and some of it is not. So we're going to see high dissolved organic carbon in general in places with higher population density. And we will also see by inference that the total organic carbon goes up higher particulates. And the particulates become important in some cases. We'll talk about the particulates, especially when we get to talking about estrogen. So, but for now, we're just going to focus on the pollutant dissolved organic carbon, because this is the stuff that's the most labile, the most reactive, the most sensitive for biological oxygen. So there's a whole bunch of different considerations to think about. So this is one consideration for a total variation in dissolved organic carbon content at the watershed level. And this is just an example I pulled out of the literature. This is a place in Africa where land use practices have been evolving over time and are trying to understand the variations in dissolved organic carbon. And so one of the kind of considerations is you have an amount of organic carbon that's in the water that's flowing through, and for that to change dramatically over short periods of time, that usually implies a transfer from reservoirs adjacent to the water, meaning leachable dissolved organic carbon from soils is one common place. And so the relationship between this and this can be modified by a combination of human activities as well as natural variations, how much rain, the characteristics of the soil, especially if human activities are changing the soil properties. Think about going from a natural soil to an agricultural soil, changes in topography, for instance, flattening areas out for fields, or something that isn't included on here, but deforestation, which will change runoff rate. And these things, these parameters interact together independent of population. They're more of a land use characteristic that, in a sense, you can't just turn up one knob and affect one other thing because these things vary with each other. So there are exchanges, and these are very specific to every setting. This is not a general scenario, but it's one that works for that. So another thing to think about is a time scale, right? So if we're on a watershed level, large watershed, not sort of Hawaii Manoa style, but a larger area, we're looking at variations in organic matter content in the water, or almost any other parameter in the water over sort of decades. We're trying to figure out, well, why is it changing so much? We have to think about things that happen over a range of spatial scales and a range of temporal scales, right? So some things vary very quickly, seasonal, some things vary annually or decadally or whatever that is, centennially, and vary over different ranges. And this happens to be for a forested watershed in another ecosystem, a parkland, where there are various management practices going on. For instance, there's some grazing and some burning in some areas. There's some ecological restoration in other areas. There's changes in behaviors of people using the park for whatever recreational activities they have. And then superimposed on that, we have things like climate change and carbon cycle variations that are being forced by anthropogenic climate change. And these things all interact together with each other. And again, this is a specific example from a specific place, but I want you to think about the fact that if we go to a place at one point in time and measure something, we're measuring the combination of a whole bunch of different effects, things that may have changed recently and things that change over longer time scales, and things that might be addressable by looking at one particular place versus broader scale issues. So this is a conceptual model for that particular ecosystem, and you can see there's a huge number of things on it. And the point is not to go through, you can look through it in the lecture notes if you want, but to see how many different parameters interact with each other to affect the amount of dissolved organic carbon. And there's a combination of things here. There are land use practices, cultural practices, stewardship of the land, changes in population demographic things, for instance, and targeted activities like we are going to do less of this or more of that to try and affect the kind of total carbon content in the runoff. I blow up a couple of these areas for you, these two little boxes. So for instance, it's I realize a little bit fuzzy, but you can see stuff here like how much burning is happening, how much erosion is happening, how much erosion is a function of how much bare ground there is, how much bare ground there is a function of things like how many sheep are we, or the number of sheep and how often are we allowing them to graze, etc. And then you've got, changes in what's in the environment, and down here we've got things like, what's growing on the land surface, more scrub, less scrub, reduction of vegetation, etc., etc. And these are things that might be driven by climate, they might be driven by human practices, they might be driven by both, they might be driven by other parameters as well, but all these things kind of work together over those variety of timescales to affect the organic matter. So it's a rather complicated thing. Nevertheless, we kind of go back to the original statement which I made, which is that population density in general relates to higher organic matter content. You can see that on these slides. So this is the total organic matter content dissolved in milligrams per liter, and this is kind of population density per meter squared. And so what you find is that I'm sorry, actually this is flow rate of a river. These are flow, these are population density. So let's look down here first. This is the number of inhabitants per meter squared, and this is dissolved organic carbon on a log scale, and you can see it increase, and in two different watersheds. This up here is another related property, which is related to how fast water is flowing in an environment, and the organic matter content seems to be highest when the water is flowing the slowest. You might say, well, why is that? If you think about water flowing on average flow rate, there's aeration, and aeration allows us to reoxygenate water, which allows respiration to go at a more maximal rate to help kind of break down and decompose organic matter. This is just the same plot, but one over the flow rate. So some combination of high population and slow, low flow rivers would together give us the highest organic matter content. So this is a related diagram showing you the two nutrient elements we talked about last time, nitrogen and phosphorus, again, versus population density. And you can see there's like a huge range there, as we talked about last time. There's some rivers that flow through very agricultural regions that tend to have much more excess nitrogen than phosphorus. We have other regions where water's flowing through kind of industrial or urbanized areas. They tend to have more phosphorus. Both of these yellow lines kind of represent the Redfield ratio relationship. And nevertheless, even though there's spread and there's complication, you do see that as population density goes up, nutrients go up. So now we know that nutrients go up and organic matter goes up, and both of those things cause a stimulation in photosynthesis and respiration. And both of those things ultimately lead to high biological oxygen demand, which means that the waters themselves, once they get to a place where they're stagnant and they can't aerate, go down to low oxygen content or hypoxic conditions. So here's some more seasonally driven variations in how organic matter might vary in a setting. And so we've got dissolved organic carbon and dissolved inorganic carbon on this diagram. And you can see here that, so this is DOC, dissolved organic carbon. This is DIC, dissolved inorganic carbon. This is basically carbonates or bicarbonates, etc. And you can see the exact opposite relationship between runoff rate and dissolved carbon, right? And so here, in the case where runoff is high, we have more exchange of soil water with the surface water system, which allows leaching of some fraction of the soil humus, especially the fulvic acid component and smaller molecular weight dissolvable carbon compounds that would be residing in the pore spaces. And when water isn't able to flow so easily through that soil, it pretty much stays there. But when we add a bunch of extra water and we add a gradient that allows us to accumulate surface water, we're going to wash out some of that organic. That's kind of the opposite with the dissolved organic, inorganic carbon, because this stuff is basically set by equilibrium with the atmosphere. And the more water we put into the system in a small amount of time, the more we're just going to dilute our inorganic carbon. So this is just one way in which seasonal variations can also affect the organic matter content in a place. Now, if we're in a setting that's kind of on the edge of, being able to have a high BOD hypoxic situation when we have just enough over some threshold value of organic matter, then that might vary seasonally from place to place. So that makes sense. Okay, so this is another example showing you broader scale now at the scale of 2 watersheds, what happens with the flux of stuff off the landscape. And so the 2 watersheds here, they're adjacent to each other. One of them is forested, one of them is deforested. They're basically in the exact same environment, exact same soil type, same hill slope. The only difference is that land use practices have changed. And so we can see 3 things over the course of time. These are measurements that were made for 3,000 days, starting in January and going to whatever that is. I think it's like not quite, whatever that is, 7 years, something like that. And so you can see changes in organic carbon, changes in aluminum, and changes in nitrates. The aluminum is, this is basically insoluble particle flux. We're measuring clay particles coming out of the environment. And the up and down variations are really a function of sort of amount of rain and flow rate coming across the environment. And so one thing that you can glean from this is that the dashed line, which is the forested watershed, and the solid line, which is the deforested one, that the deforested one is more productive in particles, right? More particles wash off because we've lost that hill slope stability that comes from having it forested. Not every year is the same, right? Obviously, some years there must have been more rain, more intense stuff going on. These were heavy rain years. Maybe that was a heavier rain year. And we see that offset. In some cases, like in this case, there isn't much offset. In this case, like a factor of 2. Then when we look at the nutrient flux, right? So we're looking at chemicals that are in the soil that have been in that soil as it has developed over centuries to perhaps a millennia. Then we go and we change things. And we can see that we have seasonal forcing of nutrient flux coming out, just for the same reasons that we had on this slide back here, soil water connectivity, for instance, but it's very low variation annually in the forested watershed, but much higher. The shapes of the peaks are similar, but all of a sudden, without having that intact ecosystem, we're pushing through a lot more water and we're shedding a lot of our nitrate out of the system. Then you come down to dissolved organic carbon, you see basically the same thing. The unforested or deforested watershed is pushing a lot more carbon. So now this becomes a little bit complicated because we know from this that there's also a particulate load. So that when these particles get into the water, they start transporting, they are not only representing high BOD and representing a stimulating nutrient flux, which can cause photosynthesis, but there's this competing factor of particulate load. Particulate load minimizes to some extent the amount that light can penetrate into that environment, which may therefore affect the ability of the nutrients to cause a stimulation of photosynthesis. And that will change along gradient in watershed depending on the flow field. As particles start to settle out, then we might see more stimulation further down in the watershed. For instance, in a lake that's intersecting one of those streams. So there's a lot of stuff here I know I've kind of put together. And I guess the take-home message is that there's organic matter that gets introduced into the environment as a function of a whole bunch of different parameters and a whole bunch of different time scales, some of which are dependent on human activities and the population density, some of which are dependent upon the ability of organic matter to break down, for instance, as water is flowing through an environment. And some of those things are affected by bigger scale processes on the planet, such as variations in climate and whether they're anthropogenic or not. Now, on top of all that, when we flux organic matter off the land surface, it's not all equally rich, right? So you can imagine the whole pantheon of chemicals. Some things are really easy to break down. Some of the things are very difficult to break down. And for the sake of argument, we're just going to talk about two pools of carbon. One is called labile. Labile is just the organic chemistry term for meaning reactive, easy to break down. And the opposite of labile is refractory, not easy to break down. And what we're really talking about here are chemicals that can be acted upon by enzymes within heterotrophic organisms that would use them as a food source because they fit the shape of the particular enzymes that are involved, for instance, in the TCA cycle that we talked about before, versus chemicals that don't. So if you can imagine, you got a waste stream of organic matter that's been feeding into an environment for a long time, and it's got some of this stuff and some of this stuff. This stuff will get broken down, and this stuff won't. So it starts to build up. And oftentimes these chemicals can be more toxic to organisms than these, in part because they're less water soluble, in part because they might be halogenated. We'll talk more about toxicity of organic chemicals in a couple of weeks. But so you can imagine the integrated effects. If you're in a watershed that's had organic matter coming into it from human land use practices for a century, and then we go and look at, for instance, sediments in a lake, or we look at organic matter in soils that are receiving this sort of human-induced waste stream, we're going to see a buildup of these. So that might be, even if the total organic matter isn't that high, we might find high concentrations of the refractory stuff because over time it just hasn't been decomposed. So this is two diagrams kind of showing you a temporal variation in the Rhine River of organic matter. And this over here, this is just sort of added off to the side. This is sort of the amount of phosphorus that's been mined in the world and the kind of buildup of phosphorus concentration in a lake that's on the Rhine River, about kind of 2/3 up to the headwaters. Just to give you context, right? We know that this is an agricultural region of Central Europe, and extra phosphorus applied to the fields causes extra fertilization, which causes some leaching of extra organic matter out of the watershed into the river, which contributes to high organic matter content increasing over these years, but doesn't account for most of it. And so now what we look over here, right, is we see the flux of various kinds of carbon increasing, right? These green lines are going up a lot, and this red line is not going up that much. And so you can see here, this is the flux of degradable carbon. That's the labile stuff, the stuff that's like, yeah, it can be broken down. This environment is able to continually degrade this carbon that's not refractory. But if we look at this green, this is the refractory carbon that is building up in the waters and the sediments of this river. And we can go into some specific compounds here, like we have, consumption of organic chemicals excluding hydrocarbons. These are some of the more refractory chemicals. You can see how much more they're building up. They're a component of the labile flux. You can also see the gross domestic sewage discharge. Kind of, this is increasing over this period, but these refractory chemicals are growing very, very quickly. This little inset is basically looking at halocarbons, which are part of, when they're high molecular weight, at least part of the refractory pool. And this is now not versus time, this is versus kind of distance along the river. And you can see the concentrations of these things building up, especially aromatic halocarbons and various other, halocarbons that are non-aromatic, both of them building up in the water as we go along the flow path, because there's some amount of them in the discharge, but the labile component is being dissolved away, so this other stuff tends to accumulate. Okay, so that's sort of a summary of all the things that happen with dissolved organic carbon and that vary from place to place. And we can find specific, and we'll talk about a couple of specific examples in a second. But now I want to switch for a second and talk a little bit about how does organic matter get into an environment and how does that impact things. And as I mentioned at the beginning, we've got point source and dispersed sources. Dispersed sources tend to have watershed-wide level impacts that we might see vary on things like seasonal and broad spatial scales, but the point source ones tend to be ones that we can identify because there are some very, very specific patterns. So if you recall, I showed you this diagram last time, which looks at the sort of cycle of photosynthesis, respiration, oxygen consumption and production, carbon dioxide consumption and production as a function of either nutrient flux or organic matter flux or both, right? And with P representing excess photosynthesis, R representing excess respiration. So now these are some plots of discharge of chemicals at a point source, meaning a specific discharge from a pipe into a flowing river, and then looking at the river is over here and the lake is over here. The discharge is coming in and we go along the flow path. What happens with respiration and photosynthesis? Remember, whenever we have respiration in excess of photosynthesis, we're going to consume oxygen. And when we do that, we have, that's the high DOD, we go to eutrophic conditions. So if we look here, the waste stream of particles comes into the river, and so photosynthesis is increasing upward, with that, thus this up arrow, and respiration is increasing downward, thus this down arrow. The first thing that happens, we put in some particles, we occlude the light, and so photosynthesis goes down, right? At some distance downstream, it's going to increase, and it's increasing more than it was before. And this is on the basis of this kind of simple model, assuming that the particulate load that's and the dissolved load that's in this waste stream has some nutrients in it. Those nutrients get liberated by the decomposition of the organic matter, so they stimulate more photosynthesis. So we get a bump in photosynthesis, which then dissipates as we go downstream. But look at the respiration. It has this huge peak right where the waste stream is because there's decomposition of the labile components of that waste stream, which again dissipates at some point downstream. And there could be two components of the respiration. There's the respiration of the primary effluent and the respiration of this newly produced algal biome. Does that make sense? So, and the shape of these things, the amount downstream, all depends on things like how fast the river is flowing and how turbulent the flow is. The more turbulent the flow is, the more we tend to disperse particles and keep them suspended and limit the distance, or extend, I guess, the distance over which this happens. But we also cause aeration, which limits the impact of this on the oxygen concentration. Now, this is just an example of what happens when you drop a waste stream into a lake and surface water. So now you're looking at respiration increasing that way, photosynthesis that way, and there's depth in the lake. And what you tend to see is that in the area around where the waste stream has been introduced, the respiration goes up because the respirable organic matter increases. And because of the high particulate load, photosynthesis is potentially suppressed. But because in a lake, particles tend to settle more quickly, we still see relatively high photosynthesis, but at some depth below, we see an enhancement of photosynthesis. And this would be because respiration on those falling particles may cause the sort of very upper part of the hypolemnian to experience like an extra slight increase in nutrient content, which would give it a little bit extra, boost in photosynthesis. So now we come down here, we can look at the dissolved oxygen content. So in the case of the river, right at the place where, or just downstream of where the waste is introduced, the oxygen is low, right? And how low it is a function of all these variables we've been talking about. the proportion of waste to the amount of river water, the flow rate, the aeration rate, etc. And we see the nutrient content going up. And in, you know, the lake, we see not much effect at the surface because of exchange with the atmosphere, but as we go down with depth, adding waste, organic matter waste into a body of water that doesn't flush very often is just going to contribute to the rate of eutrophication at that depth. Okay, so this kind of point source loading, which is kind of what I want to focus on now, has multiple effects. Right at the area of input, there can be physical and aesthetic things like what does the water look like, what does it smell like, impacts, and there can be major ecosystem disruptions. And then somewhat downstream of the point source loading, we can find superimposed effects such as the re-enhancement of biological activity in the form of photosynthesis, which itself can then have a secondary downstream effect in the form of representing a secondary high pH. And it all depends on the specifics of the environment. So this is kind of a simplified look at, you're looking kind of down in this thing. It's a plan view map of a river flowing through, and there's a source of organic waste, and it's coming out of a pipe, and it's going into a river. And so, and the river's obviously flowing this way. And so you're seeing this sort of depiction of a perturbed area of the river that at some point downstream kind of recovers. And that recovery rate is a function of all those parameters we just talked about. But now if we look at that sort of simplest scenario that will happen is as we're going down river and we're looking at the concentrations of various things, right? And so here is the BOD, just the organic matter stream. It's highest here and it's going down. And it's going down for two reasons. It's going down because part of it's being decomposed, and it's going down because of dispersion and to some extent settling of some of the particulate components. So at some point, this and the shape of this curve totally depends on where. Now we look at the oxygen concentration, which is shown here as DO in the green line. It comes into the zone and it gets depressed to very low values somewhere downstream. And that's because it takes a little bit of time for the respiration of this material to kick in, and then it recovers. And it recovers from a combination of re-aeration and enhanced photosynthesis, which is coming because the breaking down of this BOD is liberating some nutrients. And that doesn't happen in all cases because some BOD doesn't have the nutrients in it, but in cases where it does, then we're going to see a faster recovery of our dissolved oxygen because of that photosynthetic material. So we can see that visually in terms of changes in water clarity and water color. So for instance, the places where we have enhanced photosynthesis, we'll see an algal bloom, that'll show up as green. And we will also tend to see an increase in downstream turbidity as we move through this gradient because the decomposition of this organic matter is adding to cellular biomass. And in some cases, that is contributing to the occlusion of the water, whether it's respiring organisms or photosynthesizing organisms. So in cases where the BOD is really high and our river isn't flowing very well, we can go eutrophic. And just like the discussion we had near the end of last time, where a water quality management person might say, well, how much phosphorus can I stick into an environment and not have it go eutrophic? We can also do calculations to say, well, how much BOD can we put into an environment and not have it go down the redox line, right? And these depend on a bunch of different parameters, all of which we've talked about, but there's one other parameter, which is the kinetics of biological decomposition, which in a diagram like this, we're assuming is sort of instantaneous, right? We add our waste matter in there and respiring organisms start to decompose it right away. And they don't do that. They take a little bit of time, and we'll look at the effects of that on a series of calculations coming up. So this is just another depiction, again, a plan view look at, you're looking down on a river that's flowing from top to bottom and a waste stream. And the important thing to note is, I mean, obviously there's this transition in the particle content of the water And in this case, where it says septic, noxious odors, floating sludge, this implies very high concentration of organic matter and reaching the point of anoxia, right? So that we start to smell things like the reduced sulfur and those kinds of things. That's an extreme condition. But what you find, interestingly enough, is that on either side of this, there are changes in the aquatic ecosystem that are different depending on which things we look at. So for instance, if we look at fish or invertebrates or plankton or bacteria, we see more or less effect, especially any organism that is sensitive below about 4 milligrams per liter to oxygen concentration, including fish. We're going to see them completely gone here, but we're even going to see changes in the population potentially because fish can't migrate through this zone upstream and downstream of the contamination. We see that even more in the kind of variation in the organisms because there are some resistant organisms that are able to kind of withstand, maybe not right here in the center, but on the sides, so that we may see a difference in what's living on the seabed. And if you think about some of these things as being at the base of the food web, they can then have impacts on the higher organisms in that ecosystem long term, right? As long as this is happening, you can shut this off, and then maybe things will recover over time, depending on what's left in the sediments and whether you leave them present. But there are a lot of impacts. That's kind of all I wanted to emphasize here on the ecosystem of it. So now let's look at a couple more of these kind of time variations in things. This is the Rhine River again. This is sort of poster child of human impacts on a large riverine system. That there have been people living around this thing for thousands of years. So this is a time slice from the sort of 50s to 1990, and this is looking at the dissolved oxygen concentration over time, right? And I've highlighted in red what the saturation value is. And you can see that over time, it was kind of going down and down and down. Think about that plot I showed you with the labile and refractory organic matter a few slides ago. That's basically the impact of putting a lot of untreated sewage as well as agricultural runoff that hadn't been mitigated. And that was pretty common up through the 70s, and in some places, even later than that. But in this particular case, they started to enact some stricter measures. So around the 70s was the time that some places started to go from what we call primary to secondary sewage treatment. We'll have a whole week about sewage treatment later, but primary means you're basically just taking out the solids. There's not much treatment. And secondary means you're actually doing something to reduce the organic matter load and the nutrients in it. And so that distinction in a lot of places helped to improve the load into watersheds. And so we start to see a recovery here. But you can see it got to the point where, yeah, it didn't get to hypoxic, but it got pretty low in places along that river. And that's not uncommon. And I don't mean to pick on the Rhine River. You can find the same scenario in other places. And we'll talk about some other examples in a moment. But the first thing I want to do is go through this idea of rates at which decomposition happens. So this is kind of the same diagram. This is from your text, but that's basically the same thing as is shown in this diagram. It's basically showing you've got an oxidizable pollutant, BOD, and you've got dissolved oxygen, and you've got this area that we call a DOX lag, meaning it's been reduced, and it's been taken all the way to zero, so it's true anoxic, so it's calling it a septic zone. Septic zone in general, meaning that we've got high sulfur content. And the assumption of this in this diagram is that the organic matter is being broken down instantaneously. That's something called a Streeter-Phelps model. And we're going to go through the Streeter-Phelps model in a second. But this is the simplest quantitative treatment of the dissolved oxygen content evolution, but it assumes that every mole of organic matter that you stick in breaks down instantaneously, right? It doesn't consider the fact that maybe some of that stuff is refractory and some of it's labile. It doesn't consider the fact that different places have different consortia of microorganisms that may break down organic matter at different rates as a function of things like temperature, availability of substrate, or what have you. And so it turns out the more realistic scenario is to do an incubation of the organic matter using the local organisms to see how different the rate of decomposition is for a particular place and in the presence of a particular waste stream. So what we'll see is that this tells you the worst case scenario, right? Because it assumes the most rapid decomposition of organic matter. And if you use a more realistic scenario, you can usually increase the sort of amount of waste stream without causing anoxia or even hypoxia. So here's like a little Streer-Phelps problem. Basically I just set this up, we've got some organic water, organic matter waste stream, and it's giving us a concentration of 6 milligrams per liter of organic matter. And we say, okay, the temperature is 25 degrees C, and that's important again because of the oxygen saturation value being 8.6, which we talked about last time from the nomogram. If this were colder, there'd be more oxygen in the water. If it were warmer, there'd be less oxygen in the water. So we want to ask ourselves, well, will the water become hypoxic by complete digestion of this stuff in a Streeter-Phelps model, meaning an instantaneous decomposition? So things we need to know is, okay, if it's going to go hypoxic, then we need to get down to a certain concentration of 2 milligrams per liter. So we need to know how much oxygen is present at 25 degrees C, that's 8.6, right? And so then we're going to ask the question, is there enough carbon here that using the stoichiometry of the Redfield ratio, if we decompose that carbon and decompose oxygen, will we reduce the oxygen from 8.6 down to 2? That's really what the question is. And if we do, then yeah, it's going to go hypoxic. And if we don't, then it won't go hypoxic. So this is the same stoichiometry we talked about at the end of last time. We've got our total organic matter content. Oh. Thank you, computer. And we can do a simple calculation, which is we've got our 6 milligrams per liter of organic carbon. We're going to instantaneously decompose it. We've got this stoichiometry that we talked about last time from the Redfield ratio of 140 milligrams of oxygen are consumed in the respiration of 100 milligrams of organic matter. So we can just convert this in quickly and say, yeah, 8.4 milligrams of oxygen will be consumed by putting in 6 milligrams per liter of total organic carbon. And when we take 8.4 away from 8.6, we end up with 0.2, which is 2.3% of saturation, which is hypoxic, right? But this isn't how it usually works. This is like I say, it's the most extreme calculation. So there are several phenomena that go on that can affect the rate of organic matter degradation. Some of them are biological, and some of them have to do with the rate of aeration and mixing and diffusion of the plume in a stream. And these are, all different from different settings and so forth. And there are, in fact, things that if you're a sewage treatment plant or someone else who's producing an organic matter waste stream, there are things you could do to mitigate your impact by, for instance, instead of discharging all your stuff in one place, spreading it out over various places. Not that that's the best scenario, but it's at least a minimum scenario. And so what we really need to do is think about the rate at which organic matter decomposition is happening. Because if it's slow compared to the rate of input, then that waste stream of 6 milligrams per liter may not actually cause hypoxia because we may have enough downriver transport and dispersion to prevent ourselves from going hypoxic. So one way that BOD is measured from the biological perspective is to do like a 5-day incubation. Take some of it, sample it, and measure it in the lab and see what happens, right? And in those scenarios, for biological decomposition, the sort of first order scenario that we use is what we call a first order kinetic rate law, which means that the amount of biological oxygen demand, the amount of labile organic matter present at any given time is the amount present at time 0, e to the minus kt. This is the exact same form that radioactive decay has, where t is time. K in this case is a term that tells us something about the reactivity of the organic matter, right? In a radioactivity sense, this would be the half-life, and that doesn't really change from setting to setting. K is highly dependent on what organisms are present and how do they respond to environmental parameters. So, and this is a simplification as well, but it's a much better way of looking at the decomposition than just assuming it's instantaneous, right? And so if we do that and we make this measurement from the decomposition rate from the incubation, then we can sort of say, well, for this particular place, will it happen? And so I've just thrown in a typical value, right? You can put in whatever value you want, but for the purposes of the argument of putting in this value of 0.2 milligrams per day for the K constant, and so we can write an equation for this. And we're going to talk in coming weeks about the relationship between water flow and chemical diffusion and other production and decomposition terms such as biological decomposition, chemical reactivity, and biological activity, which collectively are defined as the diffusion, advection, transport equation. I don't want to get into the details of that because it's fairly complicated today. I'm just going to present it to you that if we look at the rate of change of any chemical, but in this case, we're talking about oxygen with time, there are three things we have to think about. We have to think about how much is our chemical, in this case, oxygen, diffusing, how much is it kind of moving with the river water, and how much is it being affected by reactions, okay? And in this particular case, with a very high BOD waste stream, it turns out that these terms don't matter that much, right? Unless the river is just racing through, the transport is not going to really affect oxygen very much. And diffusion happens over very small time scales anyway, so that to a first order, the change in oxygen boils down to the reactions. And I will just point out that if we go back to something like this diagram here, it's not even considering the diffusion and advection. It's just considering the biological decomposition. And as I say, we will talk about the diffusion advection equation in more detail coming up. But we can write this equation, right? And we can sort of rearrange these terms. So for instance, the change in concentration of any chemical like oxygen as a function of advection is basically the rate of flow of the river times the concentration in the absence of any other process. That's what this term is. The term for diffusion is basically not even included here because it's so small, it happens over small spatial scales. But then I've included, for realisticness, two reaction terms. One of them is the coefficient of reaction times the biological oxygen demand, meaning this. And the other one is a competing term, which is aeration, right? In a very realistic scenario, not only do you have organisms breaking down stuff and taking some time, but you also have oxygen exchanging with the atmosphere. So this is the kinetics of oxygen saturation. And again, we'll look at this in a little bit more detail again later in the semester. But the amount at which reaeration can take place is a function of how undersaturated you are. So the more undersaturated you are, the more difference measured oxygen is from real oxygen, the faster it will tend to diffuse back in. And there's a diffusion constant for that, which is temperature dependent and kind of dependent on Henry's law. And then we've got this term that we just talked about, the biological oxygen demand. So we can rewrite this thing and basically say that the oxygen at any point in time is going to be the amount of saturation minus the combined effects of the aeration term and the BOD, and then we can just go through and solve it again. It's a little bit more complicated to solve, but I've made a table here sort of showing you the values, typical values for some of these parameters. And so for instance, if we have an A of 0.02 or an A of 0.002, right, A being that reaeration term, we change the conditions over which the aeration happens. And if we have an A of 0, which is a very fast aeration, you can see that the oxygen gets higher and higher as we go, right? So kind of low, kind of high, kind of low, getting lower as we go. And so if we have a 0.2 for this value, and we can take these oxygen concentrations, any one of these ones in the table, and we can subtract them from 8.6, right? And then look at whether or not that is below 2 or not, which is the definition of hypoxia. And what we find is that in all of these cases, when we put in these realistic parameters, they don't go hypoxia, right? Because we didn't use the Streeter-Phelps assumption. So in a way, you might say, well, this is kind of a dangerous set of calculations because it means that a water quality management person might say, oh, well, great, I'll just crank up the amount of waste I'm putting in the environment because it's not going to decompose. But I think the way we have to think about this is hypoxia is like the worst case scenario. Well, maybe anoxia is even worse, but getting to hypoxia is something you don't even want to get close to. You want to be far away from it. And so it is true that the more refractory components your waste stream has, or the slower the biological decomposition is, or the higher the aeration rate, maybe you could allow a little bit more waste to come out. But in many cases where we have a waste stream, we don't just have one, we have multiple different entities producing organic matter into the water, and so it becomes cumulative. And the more people can do to stay far away from the possibility of making anoxia, the better. Okay, so now we're going to talk about a couple of specific examples. This is the Thames River estuary, and so I have to introduce something about estuaries to you too. So it turns out that in estuaries, we have water. We're going to have a whole week about estuaries, but we have river water flowing downstream towards the ocean, and we have salt water incurring up the estuary. And the way they mix and the rate of mixing is totally dependent on a huge number of parameters. How fast is the river flowing? What's the shape of the estuary? What's the tidal forcing, et cetera, et cetera. But there are two typical kinds of estuaries. This is salt content, salinity, as measured from a river going into the ocean. This is a typical kind of estuary. It's called a salt wedge. If you imagine fresh river water kind of flowing out, it's pushing out across the top, and tidal forcing is putting dense salty water in across the bottom. And so this is kind of the way it mixes is that if you were to go into depth profiles, you'd see that the salinity varies kind of diagonally. In estuaries where rivers are running very, very slow and tidal forcing tends to be relatively low, we find a slightly different pattern, right, where it's constant throughout the whole water column. Whereas over here, if we were to go down with depth, we go through salinity variations, and we have a horizontally stratified scenario, kind of like a lake. Over here, this is stratified more like a lake on its side. This is a condition that tends to trap water for longer periods of time, which in our current discussion, in the presence of a high DOD stream, means that the residence time of the water goes up. There's more time to decompose that BOD and more time to decompose oxygen and go in oxygen. So now this is the Thames River estuary as it flows through London. And this is in relative location. 0 is London Bridge. So this is upriver and downriver, okay? And now, so this is kind of an unfortunate place to put a big city that's been there since Roman times because the river flows in a way that traps organic matter. Think about until they invented the toilet, people taking their buckets of stuff and just throwing it out on the street and it's all washing into the river. This river received a huge amount of organic matter, labile organic matter load for millennia, which culminated in it going pretty gnarly in the 20th century. So this is, again, miles above and below London Bridge, that place here and this place here. And this is the dissolved oxygen content as a function of time. So the first measurement was made in the 1890s, and people were realizing, oh man, it smells pretty bad here around the river. And, for 10 miles on either side of London Bridge, which is, no trivial distance, and the oxygen concentration was down to 20% of saturation. Pretty low. But you can see how much worse it gets, right? This is early 1900s, mid 1900s, 1950 to 1959 is the last one. You can see that it gets completely innocuous, right? There's nothing living in this river. It's, for something like 40 miles of expanse, it's, like I say, a pretty gnarly place to be by. After that, things were enacted to improve it, and that's shown here. So now instead of looking at, time distance, we're just looking at time and total dissolved oxygen concentration at two different spots, okay? One of them, so unfortunately this uses a different scale. Teddington Weir is a dam that is upriver of the of London Bridge. So Teddington Weir is off this plot, but it's somewhere over here. But so we're looking at now oxygen concentration as it varies along a gradient with a slightly different length scale, but it's the same place. And we're looking at two different times. And so, or excuse me, two different places over time. So this is, upstream, and this is downstream, close to where London Bridge is. And so what you see is that the concentration, again, in the 1890s, it was bad. It gets much, much worse. And then they started to do some sewage mitigation controls, and the concentration came right back up. And you get the same shape of the same curve further upriver, but essentially a less extreme case. So these problems are fixable if you're aware of what they are. So this is actually a local example. You may have remembered this from about 10 years ago, where there was a pipe that broke. This is like a Matson pipe that's used to transfer molasses, and it was going underneath the harbor, and it cracked open, and it was a lot. It was 230,000 gallons of molasses. So if you think about labile organic matter, pure sugar going into the water, it's about as labile as it gets. And this is basically the algal plume. This is also water that doesn't exchange very quickly. And so it was a big deal here. There was huge impacts, ecosystem impacts on number of fish killed. I mean, this is a story from the local news where it's like, oh, maybe it's the worst environmental disaster ever. I don't know, because we've had some other pretty bad ones here too. But it's an example of how high BOD waste streams can have a very quick impact on an ecosystem. And especially here, because the water temperature is relatively high, the dissolved oxygen is very low. So the last thing I want to talk about is hypoxia in general, and hypoxia can come from a case like that, where it's organic matter in, or it can come from nutrients, or it can come from both, right? And so this is kind of an infographic that summarizes what happens in a coastal zone where we've got runoff that has some amount of organic matter in it, some amount of nutrients that gets into the shallow water column. It causes a combination of fertilization and algal productivity, which makes organic matter that then falls down out of the water column, plus respiration of the organic matter in that waste stream. And in a stratified water column, which is what we commonly find in bays and inlets, estuaries, coastal zones, where there's a strong stratification, primarily because of temperature and secondarily, in some cases, because of water flow, the upper water may stay oxygenated, but the bottom water goes hypoxic because of this organic matter stream. And as I say, the amount that it happens in different places from different causes is a function of, well, what's in the water? Is it mostly nutrients, or is it mostly organic matter streams? But this has a major impact on ecosystems, especially fisheries. Think about shell fisheries, crustacean fisheries that commonly happen in coastal areas. That because the oxygen concentration goes low, we see it happen. So this is a plot from a paper that basically shows you, for instance, several different things. Places in the world where we have what dead zone is, just that means hypoxic or lower, which is where we stop to have macrofauna in the water. So you can see lots of documented places around the world. Some of them are more persistent than others. This doesn't mean that the entire eastern seaboard and the Gulf is always hypoxic. It means that during periods of time during the year, it can be. And there's no coincidence that the highest number of these things are in the most whatever you want to call it, developed countries that tend to produce much higher amounts of waste into the environment. And these areas in blue are areas where coral reefs in that region, so obviously that's just restricted to the zones where corals can grow, and basically the tropics, seem to be impacted by the influxes. And you can see, there are some places where we know there are documented hypoxic zones, and there are big coral reef impacts. So deeper the blue, the bigger the impact, the lighter the blue, the lesser the impact. Places where there's inferred to be relatively high impact. And this is probably something that's only going to get worse as the planet warms, the oceans become a little bit more acidic, both of which place stresses on coral reefs. if you give them these high BOD scenarios and corals can't move, then that ends up potentially causing more impacts. This is another example. It's kind of a classic example. This is Chesapeake Bay, which is kind of in between, what is it, Virginia, Delaware, and Maryland, and Washington D.C. is in there somewhere. This place, when whoever it was that came here, the British and whoever else, it's like, whoa, this is an awesome shell fishery and a place where there were lots of other shallow water fishes. You've got all these rivers kind of flowing in, and it's this very tidally forced, complicated estuary bay system, which doesn't flush very well. And you've got all these municipalities around it putting organic matter in it. And so this has two things on it as of, in early 2003. This is the concentration of dissolved oxygen, yellow being 0, right, completely anoxic, red being 0 to 1, brownish or purplish, whatever that is, maroon, 1 to 2. So everything, those are all hypoxic. And you can see here, they're like, yeah, most of that bay is hypoxic. And so whatever kind of shell fisheries, oysters, clams, quads, whatever it is, that they eat there, those are gone, right, because it's gone hypoxic. And you can see that these places aren't quite as bad, right? If there's no places that are over 8 being saturation, but we got some places 4 to 8, right? So they would still be officially oligotrophic in this blue zone. So we're all, over here by the mouth and kind of coming up into here. But even here, this is impacted, right? Anything less than 4, you're starting to see major impacts on your microphone. And so you can macrophone and you can see the sort of number of fish caught in different places. And yeah, fishery is still okay over here, not okay here. And this is specifically due to non-point source loading of organic matter and nutrients into this watershed. Think about every one of these little rivers carrying some stuff into it. And what's causing the distinction between things being kind of okay here and not okay here has more to do with water flow rate and flushing and reaeration, tidally driven. So another place famous, if there's any place that you've heard of coastal hypoxia, you follow that news, is probably the Gulf of Mexico. At the mouth of the Mississippi River, we've got the kind of watershed load of the entire continent carrying a bunch of stuff. And this is sort of annually from 1985 up until about 2014, how big the hypoxic area is when we look in plan view on the map. And you can see it's not the same size every year. There are all those factors we've been talking about, flow rate and land use practices and climate, that cause fluctuations. But you don't have to glance that hard to see that there's more tall sticks over here than over here. There may be some worse years up in here. The latest data suggests that this isn't like peak and coming back down. There's natural variations, but it's still a significant problem. And some years are worse than others. All of these areas of hypoxia, right? This means literally less than 2. That has major impacts on marine ecosystems over a big area. And that's all pretty much driven by Mississippi River runoff. So this is a map showing you 3 different points in time: 1986, 1990, 1996. All of these are in the summer. In the summer is when the water tends to stratify the most here. It heats up, and so the upper part of the water column becomes much less dense, and it floats on top of the rest. And these are a bunch of depth profiles at different times. So we've got temperature and salinity, and then highlighted in green is the dissolved oxygen content. So what you see is that up in the upper part of the water column, the warm stuff sitting on top, it's still exchanging with the atmosphere, and down to about 10 meters or so is oxygenated, and then all of a sudden we get down to below that, and it gets unoxygenated. So the hypoxic areas are kind of highlighted in pink on each one of these profiles, and those are specific stations. These stations are highlighted here with dots. And so when we talk about the size of the hypoxic zone, we're talking about how many of these stations, when we go kind of laterally along the coast, go to hypoxic conditions in the bottom waters. And this is like a more recent depiction of this, showing you what it looked like in 2017. All of this area is hypoxic. And so the question that you can ask yourself is, So what is causing that? Is that primarily nutrients coming out of the Mississippi River, which is draining out over here, and then currents kind of pulling it along, and it's causing photosynthesis, and that photosynthesis is then representing BOD that gets decomposed, or is it mostly organic matter? And it turns out, using satellite observations and so forth, in this particular case, it seems more to be biological productivity, meaning nutrient loading into the environment. Not that there isn't organic matter coming out that river as well, which then implies that if you could somehow mitigate the concentration of nutrients coming out of the Mississippi River, which is, again, a huge watershed, you might be able to impact this. And the fact that it's getting worse over time means that collectively agricultural practices in that part of the continent need to change. So the very last thing I'll show you is just a little bit more stuff about how people think about this problem. And it's complicated. This is the watershed, right? So the Mississippi is coming out here. The hypoxic zone is down here. This is the same thing as the last time. But look at all these different rivers that feed it. They're not all one setting. They're not all one type of agriculture. They're not all one jurisdiction. And the variations in conditions along there become very, very complicated. So the last little thing, I think I can go through it, but I'll just go through it a little bit quickly, is to look at how nutrient concentration in a riverine system affects conditions of flow. And it turns out one of the things that affects nutrient concentrations for nitrogen, at least, is the rate of exchange between the river and the river sediments, right? And so there's this hyporeic zone, which is basically a place of exchange. And it turns out that if these exchanges happen really fast, then this zone tends to stay oxygenated, and we tend to leach nutrients out of our sediments, our organic rich sediments, into the water. And if this happens slowly, then we tend to favor denitrification, which means that some of our nutrients are going back out into the atmosphere as gas, as nitrogen gas, and therefore they're not flowing down the river. So if you could do things to increase that rate, then you might have an impact on the total nutrient flux coming out of the river. This is just another kind of slide explaining a little bit more the kinds of things that affect that exchange rate as well as nutrient fluxes into the river. And this is the process of denitrification. If you can enhance this, right, having nitrate be microbially transformed into nitrogen, which comes out as a gas, and is not going to be in the water, it's not going to get into the Gulf, it's not going to cause hypoxia, if that makes sense. These last two slides are from a paper that said, okay, well, we're going to do this thing where we are going to try to model the entire upper Mississippi River watershed, right? So they're not even looking at the lower stuff down here. They're looking at, these three watersheds that are draining sort of the western, central, and eastern portions, and looking at sort of what are variations in this, rate of exchange between water and sediment. And you can see different colors obviously mean different rates. You can see here that some of them are fast, some of them are slow, but the impact of these, and this is a pretty complicated paper, but it's something that at least people have done this calculation to show, is that, so this is basically cases where we have long residence times and short residence times, right? And as I say up there, when we have long residence times, we get anaerobic conditions, which favor denitrification. Like the areas in blue should be favoring denitrification. If people wanted to do things to look at how do we enhance those rate of exchanges, we might focus on these parts of the watershed. Things that can affect that rate of exchange, certain things are characteristics of the river flow itself. But if we've started to harden riverbanks, make scoured channels with concrete on them, or anything that increases the rate at which water flows through and limits the rate of exchange, then we're just going to carry those chemicals with it and bring them into the rest of the system and coming out at the bottom. So that's kind of just a watershed level look at the scenario. Obviously, there's also the organic matter flux that is contributing to things that are happening down here. But I hope you, from this conversation this time and last time, you at least get the idea that, yeah, these are rather complicated processes. They integrate a lot of things, but once we observe problems like hypoxia in environments, whether it's in a lake like we talked about last time, or it's in the coastal ocean or river or estuary, like we talked about this time, we have to somehow figure out if there's a way of limiting either nutrients or organic matter, or maybe, you know, enhancing the rate of aeration, which is done in some places to at least mitigate the extent to which we go hypoxic. And it's never simple. There's usually, at least I should, maybe never is too extreme, but it's almost always a lot of parameters that we have to consider. So are there questions about this content? Nope.